of where we are. So as we've now seen, there historically were different ways of approaching the question of how you define quantum mechanics in phase space. Rossini did this in the 1940s and was really thinking about quantum chaos and how you define, how you would define something like chaos in quantum mechanics, where, as we know in classical physics, we think about that in terms of some aspect of what happens with distribution function on phase space. And a natural way of thinking about that is to just say, well, I can define a probability distribution, and it's most generally written this way, but say for the case of a pure state, this would represent the probability of finding the state in that coherent state, if you like, right? Wigner defined this distribution function for the case of a pure state. Again, we can generalize this definition for an arbitrary mixed state as the correct joint distribution function on phase space if you demand that the marginals are the probability distributions that you get quantum mechanically. That is to say, we demand, it must be the case, that the marginal distribution, which is given by the integral of the joint probability distribution on phase space, is what we know from quantum mechanics, the square of the wave function. And similarly, the probability distribution of finding a certain momentum would be the marginal distribution integrating the joint distribution over momentum, and that should be the square of the momentum space distribution. So if I'm going to define a joint probability distribution on phase space, that's one requirement you might demand. It seems like a very reasonable requirement if you're going to say something that is a joint probability distribution in phase space. It should have the right marginals. And that's true no matter what we're measuring in any of the quadratures in phase space. So what we have come to understand more recently is that these three kind of, and yeah, of course there's the Glauber distribution, which which came from a different perspective altogether, thinking about what kind of state would give a classical photon counting statistics, as we discussed for many weeks now. But as we've now come to understand, all of these distributions are really different sides of the same coin. They represent different representations of the state with respect to different ways in which we order x and p, because x and p don't commute. Or as we write it, different orderings with respect to a and a dagger, because a and a dagger don't commute. And so we wrote down this mathematical identity of how we can say, take any operator, in particular the density operator, and expand it in a kind of quantum Fourier transform, where we project the state onto the plane wave thing, and then that's the kind of the Fourier transform of the thing, and then we weight the plane waves by that. And that's what we got. And those plane wavy things are here. But, we have this pairing of the sigma order, so, the sigma 0 is symmetric order, plus 1 is normal order, sigma minus 1 is the anti-normal order. And we see this kind of pairing of the normal order with anti-normal order and symmetric order with symmetric order, etc. So in particular, what that means is that if I look at, say, the expected value of some observable, where that observable is some function of the canonical coordinates, some function of the space-based coordinates, then it looks like a classical average of the representation of the function over phase space, but we have this kind of pairing where we have, if we're talking about the normal ordered representation of W, we have to look at the anti-normal ordered representation of A, and vice versa. Okay? By the way, these things are sometimes known as the Weil symbols of the operator, Hermann Weil. How does he spell his name? Kind of like that. And these operators are sometimes known as the Weil operators. Right, so the representation of the density operator is the projection of this onto these T operators. These T operators themselves are Fourier transforms of the Weil operators. And we can think about them as the inverse Fourier transform of the characteristic function. The characteristic function itself being like the Fourier transform of the probability distribution. So there's lots of details here. I know it can be extremely tedious. Try to keep them straight, and it only makes sense if you actually try to do some examples of that. Okay. Now, one thing I just wanted to re-emphasize, point just we got to at the end of the class last time, just to show this little graphic again. Stolen from one of Louis Pointier's papers. We must reference that paper because. All right, let me turn this guy on. What's that?
It was just up.
Oh, was it doing it? There's something weird with the connector.
Yeah, it's working.
Okay.
It's working.
All right, let's not touch a thing. All right. So, all right, let's turn the lights off here and remind ourselves of what we're looking at. So here are some examples of Wigner functions. Okay. What we're showing here, the joint distribution on phase-space position and momentum, here written as Q and P rather than X and P, for a few different states. This state is a coherent state. Okay, it's a displaced ground state of the simple harmonic oscillator. What's shown on the shadows there represent the integral of these things over the conjugate variable. So this is the square of the momentum space wave function, and this is the square of the position space wave function, which of course we know for a ground state of a harmonic oscillator are Gaussians, right? This state is a squeeze state, right? It's this kind of state and then applying the squeezing operator to it. In this case, it's squeezed in P and anti-squeezed in X. Okay. This state is the first excited state of the harmonic oscillator, the Fock state with n equals 1. Now that's a state that's an energy eigenstate. And an energy eigenstate is, a state that where the wave function is kind of concentrated around the classical trajectory, right? If I had a definite energy, then I would be on, in rescaled variables, a circle in phase space. And what's being shown here are the, again, the squares of positions and momentum space wave functions. Yeah?
Is it displaced Fock state?
In this case, the origin is not really clear. Let's take the origin right there. Otherwise, of course, it would be something that's, I don't know if I had a displaced Fock state, would it have to be quite careful and think about what its figure function would be. I don't think it would look like that. But let's put the origin right at the center there. But one of the points I wanted to emphasize here is the following. So what's shown here are the shadows, those marginal distributions, which we know, of course, is the first order Hermite polynomial with one node times a Gaussian. And so those are the familiar squares of the wave functions in position space and momentum space. Now, if I'm going to have a node there, the only way I can do that is if somehow, and have this thing be azimuthally symmetric, is if this thing is negative somewhere. It's got to cancel some of that. There's no other way I'm going to be able to do that. If it had a node only here, then it wouldn't have the node at some other quadrature. Is that clear? So it can't have both this azimuthal symmetry and this rotational symmetry, which it must be because an eigenstate of the number operator, which is the rotation operator, and have a node. It's got to go negative somewhere. This is an example where I have a superposition of two distinguishable wave packets in position. One's at this position, the other's at that position. Now, that state, of course, is a state that would give rise to, in the far field, interference fringes. And the far field is the momentum space wavelet, right? If you take the Fourier transform of a double slit, that's what you see in the far field. And so, in order to have these two wave packets have the interference fringes, there's got to be all this negative junk going on in between them that's going to cancel this. So the non-classicality of these states is to say, if the state was everywhere positive, well then, even though X and P are not compatible observables, even though they don't meet, I can, in principle, write down a distribution function which says, I think about this just as if it were classical points on phase space. And I just don't know where it is in phase space. And I just weight what I'm going to see by a probability distribution. That it has that X value and that P value at the same time. Then it's like a classical point in phase space. Whereas if the states are negative, then that's just not possible to do. And those states then are in some sense not describable by a classical distribution of phase space. Now, one thing we note here is that there are two examples of states which, for all intents and purposes, are classical distributions on phase space. This one and this one, they're everywhere positive. Now this one maybe is not too surprising. This is a coherent state. We've kind of called the coherent state quasi-classical, right? But this is a squeeze state. And we've kind of said the squeeze state is maybe non-classical light. But that's sort of in the eye of the beholder. It depends how I'm measuring the squeeze state. If I'm measuring the quadrature, so I do homodyne detection, then I can just say that the sample I'm getting, no matter what quadrature I measure, is sampled from this distribution. And that's a positive everywhere distribution. And in fact, what you just solved, if you handed in your homework, was the problem of parametric amplification. Let me turn the lights back on. Where we said, okay, let's imagine that I have initially a coherent state. Let me just say. Now, what we just saw, we're about to derive it just to prove it for ourselves, is that this is as if there were a classical distribution of possible phasors. I just don't know which it is. With a Gaussian distribution peak here and some RMS values of that Gaussian that are measures of the vacuum fluctuation. But I could just think about that as a classical distribution. And if I start, so this is the vacuum state, if I then put this state through a parametric amplifier, then what that is a phase-sensitive amplifier, which depending upon how I have set the phase of the pump relative to the phase, I could say, let's say I amplify the P quadrature and de-amplify the X quadrature. Well, what would that do? Well, that just transforms every point in phase space. So, you know, if I look at this particular point in phase space, well, it might go to that point in phase space, right? Because the P quadrature gets amplified and the X quadrature gets de-amplified. And if I did that to every point in phase space, what would I get? An ellipse. I would just stretch these guys and shrink those guys. This is a perfectly classical description of squeezing in terms of each point in phase space gets transformed according to the phase-sensitive amplification. So in that sense, squeezing is only marginally non-classical. It is a resource for non-classical, as we said. If I wanted to look at direct photon counting experiments, those direct photon counting experiments, the statistics thereof, cannot be described by a classical theory. But if I did homodyne detection, I saw this Gaussian noise, I could simulate that completely with the classical distribution of phase space. Okay. All right, so let's do a couple of examples. Let's show. Let's we go from the polar vortex to the sonic. All right, so let's look at the example of the coherent state. Oh, I guess there was one, before I go to the examples, there was one little technical point that I wanted to emphasize here. There it is. So let me just because all these different orderings are related to one another through this kernel, the different quasi-probability distributions are related to one another. So in particular, the Wigner function is a kind of coarse graining of the P function. This is a convolution of the P function with a Gaussian. It's kind of a smearing function. And similarly, the Q function is a smearing of the Wigner function. Which is a double smearing of the P function. So as we discussed last lecture, this smearing, it makes it such that the Q function always exists. And in fact is always positive. Because it's this massive smearing out of any non-classicality, any of those ripples that we saw in the Wigner function would be smeared out by this Gaussian. Okay? And the P function in some sense has the most kind of non-classicality in it because the Wigner function is a smearing of it. But it can be things like nth order derivatives of a delta function. It says it's not really a well-defined function at all for most states. Whereas the Wigner function is the Goldilocks function. It's just right. It always exists, and it's not always positive. It really is, in some sense, what we should think about is really something to really understand, is this really non-classical or not? Is whether or not the Wigner function is positive or negative. Although, as we said, it really depends what I'm measuring. Right? Okay, so with all of that said, let's look at just a couple of examples. So let's just look at the coherent state. So there's not one way to do these calculations. I'm not even sure I know what the best way is in every case. I haven't done these calculations much in the past, but some of them are easy to do. So let's say we have a pure state, it's a coherent state, say, with that particular complex amplitude. The Q function is always easy, because the Q function is just the square of the amplitude and then normalized by pi. So that is equal to the inner product, in this case, between these coherent states. And that's a thing we know, because we've done this before, that the overlap between two coherent states is a Gaussian. And this is e to the minus alpha naught squared. Okay. Which is, I can think about as a function of the real part of alpha and the imaginary part of alpha. So if I wanted to think about this in x and p, where x is the square root of 2 times the real part of alpha, and p is the square root of 2 times the imaginary part of alpha, with that convention that we've chosen, then we usually write this as 1 over pi. This is q in canonical coordinates in alpha space. Sorry, 1/2 of that. Right. X is equal to this. So that's equal to 1 over 2 pi e to the minus x minus x0 squared over 2 minus p0 squared over 2. So this is a Gaussian with And from this Gaussian, we can immediately read off, for example, what the variance is in x and p. They're equal, and they're equal to 1 in these units. All right. So that's fine. We expected the Q function to be positive because it has to be. Or no matter what the state is, the Q function is positive, and it has, in this case, it's Gaussian with these variances. Now notice, remember in our units, the vacuum state or coherent state has a variance 1 over square root of 2. It says variance 1. So this is kind of noisier than what we'd expect from the state itself. Okay, this is maybe not the right way to say this. This is delta. I'll call this. These are the variances associated with this distribution, not the actual variance of the state. To calculate the variance of the state, you have to plug in the anti-normally ordered version of the operator delta x squared, and then average that with this, right? Because you have to match the normal order with the anti-normal order. And that would have negative stuff, which would subtract off some of that. Let's look at the p function. Well, the p function, again, so to calculate the other distributions generally is more complicated. Now, there's lots of ways to do it. One way is to calculate the characteristic function. That's typically the way, for a complicated function, that's how you do it. You calculate the characteristic function and then use that to calculate the distribution by taking its Fourier transform. And we can get the characteristic function by, say, looking at the characteristic function of Q. By Fourier transform the Gaussian. And once I have the characteristic function for Q, I could then get the characteristic function for P by multiplying them by the right e to the something or other. However, in this case, we can write this down by I. Why? Well, the P function is defined such that the state is equal to this. So what is the P function in this case? If my state is the pure state, alpha naught. It's a delta function, which is, of course, a Gaussian with an infinitely small width. And of course, if I look at that, it makes sense because I plug in the P and I, get the delta function that gives me the Gaussian. That's exactly what we write. The P and the Q are related. Do that Gaussian convolution. So the P function, if I have something that's a coherent state, it's just a point in phase space from the point of view of the P function. What about the Wigner function, our Goldilocks function? Well, again, we have many ways to do that. We could use Wigner's original formula. That sometimes is nice. We'd have to write down the x and p, the momentum, whatever the position momentum space representation of this. However, just to see how that works, let's write down the characteristic function. That's typically how you would do this, which is equal to the trace of the state with the displacement operator, with the Wigner function. And the state is the pure state. And we know how to take the trace, wave the sound, and so we can put it on that side. Sorry, that should be a D. And we did that for homework. And that's equal to e to the minus 2 alpha minus alpha now. Oh yeah, that's not right. This is the characteristic function. Sorry. We still did that for homework, even though I didn't do homework. So let's write this as a function of beta. Sorry. Always bring pencil. And we did this, and this in fact is equal to this. Right, that makes sense. Let's think about it for a moment. Okay, so that, we'll go back and look at that. That makes sense. This were the vacuum, that would be the vacuum expectation value. So that's right, that's the right limit at least. So now the Wigner function is the Fourier transform with this particular normalization of the characteristic function. Now, everything here is a Gaussian. This is a Gaussian, this is a phase factor. So the Fourier transform of a Gaussian is a Gaussian. And that's what I was jumping the gun on. And this is equal to 1 over . So this has a narrower width. In fact, if I look at it in terms of the position of momentum quadratures, what I have is this. So these are Gaussians whose widths are whose sigmas are what we expect from the vacuum, right? This is a minimum uncertainty state because in this case, delta x squared is equal to x minus of the operator. This is a symmetrically ordered thing because it's a quadrature. It's exactly how we would calculate it. And this is equal to 1/2. And the same thing for p. This is a minimum uncertainty state. So, the coherent state, its Wigner function is Gaussian and everywhere positive with the width. So when we draw these pictures of our uncertainty bubbles that we've been doing for many months now, what we're drawing are the contours of the covariance of the Wigner function. That's what we're drawing. At least when it's a stick that's everywhere positive. Now there's a factoid, which is the following. If W of alpha is everywhere positive and rho is pure, then rho is a pure state. The only state that is everywhere positive is a squeeze coherent state. Could have no squeeze in it, could be coherent state, could be the vacuum. But it's an if and only if. The only states that are, in some sense, classical are the squeezed coherent states. Yeah?
Is it important that the S and the D are in that order?
No,
Okay.
it isn't. Because if you commute them, it becomes a different alpha and a different
That's the same
zeta,
thing.
but it's also a beta. So you can push that what order. So that is to say, the only state, only Gaussian states are classical or quasi-classical. And as we'll see, hopefully, toward the end of the semester, the whole theory of Gaussian states is a very interesting one, an important one in the theory of quantum information processing. In order to do something truly interesting, we need to have a non-Gaussian state. Otherwise, in some sense, they're just a stabilizer. Yeah?
Why do you call it a Gaussian state?
Because the Wigner function for this state is Gaussian.
But is that related to?
So what one can prove, this is known as the, gosh, whose theorem is this again? Name just got in my head. Anyway, there's a name for this theorem, that's his name. Two people proved this in the early mid-70s. Proved that if the Wigner function was Gaussian, that the only way you can have a Wigner function that was everywhere positive is if the Wigner function was Gaussian. And the only function whose Wigner function is everywhere Gaussian is this one, if it's a pure state. And of course, if it's a pure state, then what is also true is the expectation value of sigma x times sigma t is a half. So if you try to make a Wigner function that was more localized on phase space than this, it's not a physical state. It doesn't satisfy the uncertainty principle. So Gaussian states will play an important role in our discussion a little bit later in the semester. All right. All right, let's do another example a little bit more quickly. So I wanted to see if I can remember whose down here that was. Hudson, that's it. This is known as the Hudson decay theorem. Right, okay, let's look at that Fox state. Q function's easy. Let's do that one first. So that's equal to the Fox-based representation of the coherent state, right? Which is the Poisson distribution. Right. Is that alpha squared? That's alpha squared. So what does that look like? So this is a function, so Q of x and p is equal to e to the minus x squared plus b squared over 2 x squared plus b squared to the n over some factors. So what does that look like as a function of x and p? Well, let's look at it, say, along the x-axis. So, say at p equals 0. This is the p equals 0 plane, for example. Just taking a cut. P equals 0. Well, it falls off like a Gaussian here. And then it has this factor. So it sort of depends what n is. So if n is, some quadratic function to the power n, and then I have the Gaussian. So what this function is going to look like is something which, kind of falls off here. Where this is, depending upon what the value of the n is. Let me draw this maybe in a slightly different way. Well, it's not a very helpful drawing. This is e to the minus average n, e to the minus average n to the power n. So this function is concentrated along this ring here. This is the ring in phase space, x squared plus b squared to the power n, but then falls off very rapidly once you get away from x squared plus b squared is 0. So if I were to look at this, perhaps a better way to look at it is this is x and p. Here is the value, say, let's look at the case n equals 1. This is the circle x squared plus p squared is equal to 1. And then everything is concentrated on that circle, and then it kind of has this Gaussian fall off around it. So the probability distribution is kind of what you would expect. It's something which is concentrated on the classical trajectory and then falls off because there's a little uncertainty. That's the Q function. What about the Wigner function? Well, once again, we'll use the same strategy we used to calculate the Wigner function for the coherent state. Let's write down what is the characteristic function. That, in this case, is the expected value of the displacement operator, where that is n. And we did that one for homework 2, some method in Math Madness. And that's equal to the factor e to the minus beta squared over 2 times the Laguerre polynomial evaluated at the square of the amplitude. So to find the Wigner function, we take the Fourier transform of the characteristic function. And that involves the Fourier transform of Gaussians with polynomials. which are other Gaussians times other polynomials, which turn out to be, again, Laguerre polynomials. So that's an exercise for Archin or something like that, some generating function of the Laguerre polynomials and all that stuff. The answer is 2 times minus 1 to the n over pi e to the minus Laguerre polynomial for alpha squared. This can be negative. So that function that we were looking at the beginning of the lecture with the ring where n equals 1, what we had was, if I look at this as a function of the magnitude of alpha, what we had is something that went like that. This is it. It's got the ring, if I looked at it in terms of azimuthal, that it dips below the origin. Yeah.
What's n? Sorry.
N. N is the particular.
There's an n on your minus.
Oh, I'm sorry. It should be to the n. Pardon me. Yeah.
So
This is alpha equals n. In case. This is for this case n equals 1. The one that we were looking at. Yeah.
I want to go back to this.
Yeah.
Your last equation there with Q. The alphas disappeared. You're looking then at the maximum value?
No, I'm sorry. I put a fast one on you. For this state, the average n is equal to alpha squared. So if I looked at the expectation value of the number operator, for that particular state, this is an eigenstate of A, that's alpha squared. So alpha squared is the mean value of n. So I just wrote it in shorthand. So this is a little bit of tedium in doing these calculations. But the important point here is that we can, once we calculate these figure functions, we can determine their degree of non-classicality in some sense by how negative they are. Now we're going to connect that right now. At least we're going to make the liaison, the segue, I should really say. So what we've been emphasizing here is whether our states were non-classical by whether or not there was a representation of that state, which we could write as a joint probability distribution of otherwise incompatible variables, variables that don't commute quantum mechanically. And if we could write a joint distribution, say, yes, there's some probability of having this x and this p, and we could write down a probability distribution, we call it classical. If it wasn't, we called it non-classical. Now, all of this was related to a single mode. That's all we've talked about, really. But, as we know, the most interesting aspects of non-classicality are related not necessarily to just one degree of freedom, but to multiple degrees of freedom. And in particular, one of the starkest examples of a non-classical phenomenon is the phenomenon of entanglement. Entanglement is starkly a situation in which we cannot write down a classical probability distribution to predict outcomes. In this case, those outcomes are related to not just a single degree of freedom, but multiple degrees of freedom. And that's where it becomes particularly interesting for us. Of course, that goes back to the heart of the foundation of quantum mechanics, the question of the EPR paradox and Bell's inequalities. In fact, historically, the first tests, as we know, the first tests of violations of Bell's inequalities were done in quantum optics. And the best tests of the EPR paradox and Bell's inequalities were done in quantum optics. And so for decades, those of us who grew up in that era, the understanding these foundational questions was really the driver of quantum optics, both in the theory and the experiment. From the experimental side, of course, it's an incredible challenge to be able to isolate and measure individual quantum systems such that you can see whether or not these violations are made or not. And the theoretical framework needs to be there at the same time. Nowadays, I'd say those, that we're getting to harvest some of that fruit in the sense of, yes, we've learned a lot, we've come to understand more deeply some of these foundational questions, but we've also come to understand that finding where that border is between the classical and non-classical helps us to understand whether or not the physical system we have at hand is a resource for doing something that's not possible if the system were describable according to classical statistics. And using that now as a resource for doing information processing, communication tasks, cryptography, communications, algorithms. So non-classicality now is thought of as a resource. And we're going to connect this other kind of non-classicality about negativity of Wigner-Fleming stuff and non-Gaussian states to this question as well of resources. So we're going to try to weave this all together. But what I want to do now is then just turn our attention then to the question of entanglement and multiple degrees of freedom and how we quantify that. Now, I know many of you have become fairly expert in this subject. Some of you have taken a year of quantum information theory and quantum computation, but not everybody. So we're going to sort of start from the beginning here and do some review as well. So bear with me, those of you for whom this is apple pie. Enjoy the little slice. All right, so let's talk about quantum mechanics of multiple degrees. So let's start from the very basics, just to wrap our heads around some of the key ideas. The simplest case, if I thought about classically, what do I mean by multiple degrees of freedom? Well, let's think about two-point particles moving on a line, okay? It's represented by canonical coordinates. So there's particle A and particle B. As position and momentum. Those are 2 degrees of freedom, as we would call them classically, right? Now, quantumly, if I wanted to describe that situation, I might write, for example, a wave function as a joint wave function for the 2 degrees of freedom, right? Of course, I can also write down the momentum space wave function, or if you want, I might even try to write down the joint Wigner distribution for these. Let's do that too. Now, if I have this distribution, then I can write down the joint probability distribution of finding the particle at position, the first particle particle A at position XA, particle B at position XB, that's my joint probability distribution. And from this, I could define the marginals. Say the marginal, what's the probability of finding the particle at XA, irrespective of where particle B is. Of course, to do that, what I do is I just marginalize by integrating over that distribution. And similarly, I can define the probability of finding the particle at XB, irrespective of where XA is, by integrating. This is probability distribution A, this is probability distribution B. This is joint probability distribution AB. Let me emphasize that by labeling everything. Now, what we know is that P, the marginal distribution, is the square of some wave function for particle A, and the distribution B is the square of some wave function for B, if and only if the joint distribution is a product state. I mean, I also have to have the momentum the right way. The only way that I can assign a state to A that's some wave function, and some state to B it's a wave function, is if they're uncorrelated. The joint probability distribution is just the product of the distributions. Such a product state is what we say is separable. So if the wave function is of this form, if there exists a psi and a phi, such that the joint distribution is just the product of them, then we say the thing is separable. If not, otherwise, entangled. So our state, if the state is entangled, then I cannot ascribe a wave function separately to each particle. There is no one wave function. I can say this is the wave function of particle A, this is the wave function of particle B. All right, so in order to, so this is what motivates this whole notion of tensor products. So I will go, starting from this simple notion of wave functions, I want to now abstractify all of this and talk about this in Hilbert space rather than in terms of the particular representation of wave functions. So, generally, given 2 degrees of freedom, the joint Hilbert space for the 2 degrees of freedom is written as the tensor product of the individual Hilbert spaces of the 2 what we call subsystems. Now this might be 2 positions of the 2 particles. They could be the spin and the orbit of a single particle, hence spin-orbit coupling. It could be the coupling of 2 spins, like the electron and nucleus, and hyperplane coupling. Any of that would be described by this kind of Hilbert space. These can be individually finite dimensional or infinite dimensional. All right, so once we define what is that, what does this Hilbert space mean? So for now I'm going to think about HA and HB finite dimensional. Of course, we're very interested in infinite dimensions as well. We've been talking about that for the last few weeks with our harmonic oscillators. But for the moment, let's concentrate on finite dimensions. So let this set be a basis for the Hilbert space HA, which is of dimension B sub A. And let the set F, where the index takes on the values 1 up to the dimension of Hilbert space B, be a basis, orthonormal basis. When we define the product basis in terms of this tensor product. Okay, so this is a basis for the joint Hilbert space. Okay? So this says that this tensor product structure just is a way of saying if we have 2 states, a state that's in a state associated with that Hilbert space and a state associated with this Hilbert space, then we define this as a state in the joint Hilbert space. So therefore the products are that way. And that product satisfies the following. If I look at, for example, the inner product of this basis vector with the state that's a tensor product, then that is defined to be the numeric product between those numbers. So with that, we can then say, we can define, if I have an arbitrary state, in the joint Hilbert space, I can write its representation with respect to this product basis. Where this is equal to the inner product of that state. Okay? Now, why in the world is this called a tensor product? Well, it comes from the theory of tensors. So, sometimes the tensor product, sometimes called the Kronecker product, sometimes the outer product. So, for example, suppose the state is, as I've written, a product state. And let alpha be the representation of the state with respect to this particular basis. And let beta be the representation of the state phi with respect to this basis. Then, this set of coefficients I and j is just the tensor product between the vector A and the vector B. Let me emphasize this is the joint state. So this is not the inner product, this is the outer product. So I took two vectors, put together to get a tensor. That's why it's called the tensor product. So written as column vectors, if alpha, so alpha, the state phi A represented as a column vector is alpha 1, alpha 2, dot, 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 alpha for the dimension of that Hilbert space. And the state phi B is a column vector of length or dimension b sub b. It has coefficients beta 1, beta 2, dot, 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 beta, the dimension of b. So, how do you take the tensor product of two column vectors? Well, here's the rule. So, let's write it down. Psi AB is equal to this. I'll leave up the AD. Tensor that. The way I always do it is this. It's alpha 1 times beta 1, beta 2, dot, 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 beta b, alpha 2 times beta 1, beta 2, dot, 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 beta d, dot, 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 alpha d. So A, beta 1, beta 2, dot, 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 beta db. That's what that tensor product is, which is just writing alpha 1, beta 1, alpha 2, beta 2, dot, 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 alpha d, a, beta, I'm sorry, beta back, sorry. So much for my handy dandy approach. Alpha 2, beta 1, alpha 2, beta 2, dot, 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 alpha 2, beta d, dot, 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 alpha d, beta 1, alpha d, beta 2, dot, 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 alpha d, beta d. Okay? And the order matters. Once you define the tensor product, you find a particular ordering of your basis. You got to keep it straight. The tensor product in the other order would have things differently.
Would it be a unitary transformation?
It would be. I mean, if you, depending what basis you choose, indeed, they are unitarily related along the same dimension Hilbert space in this case. Of course, now we can look at this. If dA is the dimension of the Hilbert space HA, and dB is the dimension of HB, then the dimension of the joint Hilbert space is the product of the dimensions of the two, as we know. Right. Okay. Oh my God, is it 6:30? Let's say just maybe 1 or 2 more words. Let me think about what I want to do. Oh, yeah. Yeah, let's just talk about the tensor product of operators. So if we have an operator, say, for some n on system A, right, like this, and some n on Hilbert space D, so these are permission operators, they don't have to be whatever operator, unitaries, you name it, it's a linear operator on the Hilbert space. Then I can define an operator that acts on the joint Hilbert space as the tensor product of those. And that has some very particular features. For example, we get a representation so let's do that in the standard basis that we just defined in terms of the product, a particular product basis of these guys. So how is that defined? Well, that's defined as these primes. This is the A part. And this is the B part. So this matrix element, OAB, IJ, I prime, J prime, is the product of these matrix elements, MI, I prime, and J, J prime. So, for example, let's consider two spin 1/2 particles. Qubits. Okay. And let's say that I take as the basis, so my Hilbert space here is the joint Hilbert space for the two spin 1/2 particles. And let's take as our basis the standard basis the eigenstates of sigma z. So the joint Hilbert space as its basis vectors those. So let's look, for example, at the observable, which is the tensor product of, say, sigma x on spin A and sigma z on spin B. And let's look at the representation of this joint operator in this standard basis, according to this rule. So that means that O is represented by the tensor product of sigma x with sigma z, right? And what does that rule mean? Well, it means exactly this, just like I did before. I put this guy inside so it's got this kind of block structure. Which is the matrix 0, 0, 1, 0, 0, 0, 1, minus 1, 1, 0, 0, minus 1, 0, 0, 0, 0. Just out of curiosity, how many people have not studied this in the quantum mechanics courses? So everyone has seen this at some level before. Okay. We're going to just review it some more because it's important for everyone to be on the same page about this. All right, so we'll call it quits for now. Where we're headed, what we're going to do is review the notion of how we talk about entanglement for tensor product spaces. And then from there, talk about what that means relative to local hidden realism, Bell's inequalities, and tests of Bell's inequalities in quantum optics. That's where we're headed. All right? Very good. I'll see you guys. Talk of where we are. So as we've now seen, there historically were different ways of approaching the question of how you define quantum mechanics in phase space. Buscemi did this in the 1940s and was really thinking about quantum chaos and how you define, how you would define something like chaos in quantum mechanics, where, as we know in classical physics, we think about that in terms of some aspect of what happens to a distribution function on phase space. And a natural way of thinking about that is to just say, well, I can define a probability distribution, and it's most generally written this way, but say for the case of a pure state, this would represent the probability of finding the state in that coherent state, if you like, right? Wigner defined this distribution function for the case of a pure state. Again, we can generalize this definition for an arbitrary mixed state as the correct joint distribution function on phase space if you demand that the marginals are the probability distributions that you get quantum mechanically. That is to say, we demand, it must be the case that the marginal distribution, which is given by the integral of the joint probability distribution on phase space, is what we know from quantum mechanics, the square of the wave function. And similarly, so here are some examples of Wigner functions. Okay? What we're showing here, the joint distribution on phase space, position of momentum, here written as Q and P rather than X and P, for a few different states. This state is a coherent state. Okay? It's a displaced ground state of the simple harmonic oscillator. What's shown on the shadows there represent the integral of these things over the conjugate variable. So this is the square of the momentum space wave function, and this is the square of the position space wave function, which of course we know for a ground state of a harmonic oscillator are Gaussians, right? This state is a squeeze state, right? It's this kind of state and then applying the squeezing operator to it. In this case, it's squeezed in P and anti-squeezed in X. Okay. This state is the first excited state of the harmonic oscillator, the Fock state with n equals 1. Now that's a state that's an energy eigenstate. And an energy eigenstate is, a state that where the wave function is kind of concentrated around the classical trajectory, right? If I had a definite energy, then I would be on, in rescaled variables, a circle in phase space. And what's being shown here are the, again, the squares of positions and momentum space wave functions. Yeah?
Is it displaced Fock state?
In this case, the origin is not really clear. Let's take the origin right there. Otherwise, of course, it would be something that's the probability distribution of finding a certain momentum would be the marginal distribution integrating the joint distribution over momentum, and that should be the square of the momentum space distribution. So if I'm going to define a joint probability distribution on phase space, that's one requirement you might demand. It seems like a very reasonable requirement if you're going to say something that is a joint probability distribution in phase space, it should have the right marginals. And that's true no matter what we're measuring in any of the quadratures in phase space. So what we have come to understand more recently is that these three kind of, oh, and yeah, of course, there's the Glauber distribution, which came from a different perspective altogether, thinking about what kind of state would give a classical photon counting statistics, as we discussed for many weeks now. But as we've now come to understand, all of these distributions are really different sides of the same coin. They represent different representations of the state with respect to different ways in which we order x and p, because x and p don't commute. Or as we write it, different orderings with respect to a and a dagger, because a and a dagger don't commute. And so we wrote down this mathematical identity of how we can say, take any operator, in particular the density operator, and expand it in a kind of quantum Fourier transform, where we project the state onto the plane wave thing, and then that's the kind of the Fourier transform of the thing, and then we weight the plane waves by that. And that's what we got. Lots of details here. I know it can be extremely tedious. Try to keep them straight, and it only makes sense if you actually try to do some examples of that. Okay. Now, one thing I just wanted to re-emphasize, point, just because we got to at the end of the class last time, just to show this little graphic again. Stolen from one of Louis Pointier's papers. We must reference that paper because. All right, let me turn this guy on. What's that?
It was just up.
Oh, wasn't doing it? There's something weird with the connector here.
Yeah, no, it's working. Okay.
It's working. All right. Let's not touch a thing. All right. So, all right, let's turn the lights off here and remind ourselves of where those plane wavy things are here. But, you know, we have this pairing of the sigma order. So, you know, the sigma 0 is symmetric order, +1 is normal order, sigma -1 is the anti-normal order. And we see this kind of pairing of the normal order with anti-normal order and symmetric order with symmetric order, etc. So, in particular, what that means is that if I look at, say, the expected value of some observable, where that observable is some function of the canonical coordinates, some function of the space-based coordinates, then it looks like a classical average of the representation of the function over phase space, but we have this kind of pairing where we have, if we're talking about the normal ordered representation of W, we have to look at the antinormal ordered representation of A, and vice versa. Okay? By the way, these things are sometimes known as the Weil symbols of the operator, Hermann Weil. How does he spell his name? I don't like that. And these operators are sometimes known as the Weil operators. Right, so the representation of the density operator is the projection of this onto these T operators. These T operators themselves are Fourier transforms of the Weil operators. And we can think about them as the inverse Fourier transform of the characteristic function. The characteristic function itself being like the Fourier transform of the probability fusion.